Hi everyone and welcome to this ARCHER2 webinar. Today we have Phil Hasnip, who is a developer of CASTEP, giving us an introduction and overview of the program. There will be time for questions at the end of the talk, but if you want to ask anything during, then you can write them in the chat or perhaps raise your hand and we can direct Phil to these questions. So yeah, without further ado, I'll hand over so we can get started.
Thank you very much, Helena. So yes, good afternoon, everybody. My name is Phil Hasnip. You haven't been duped. I'm based at the University of York. I'm a CASTEP developer. I'm also involved in the UK Excalibur project to prepare materials modeling software for exascale computing. So that's relevant to some of what I'm talking about today. And my final hat, I guess, is I'm a research software engineering fellow funded by EPSRC. So if anyone would like to ask me about that, I'd also be more than happy to discuss that. Today I'm going to talk about the program which has been, I guess, at the core of most of my research over my scientific career. It's called CASTEP. It's a first principles materials modeling program, and I will talk about what that means as well. The general idea is I'm focusing on some of the things that you might care about if you're running CASTEP on ARCHER2, and I haven't assumed too much by way of background. So I'm going to give you a little introduction to CASTEP, a little introduction to the what it's really doing, the computational aspects, and show you some performance figures, a sample application, and then we'll kind of finish. And it's probably not enough physics or chemistry for those of you who are scientists, and not enough computing for those of you from a computing background, but feel free to use the discussion time and the questions to correct those shortcomings. So CASTEP is what we call a first principles modeling program. It's based on a theory called density functional theory. It's free to academics worldwide. There was a time when that was only true for the UK, but now it's worldwide. And it's installed on ARCHER2 as a system binary. So as soon as you've got your free license, you can apply to get access to the ARCHER2 binary and use it straight away. Now, I said it was first principles. What on earth does that mean? The idea of first principles modeling is to be able to predict the properties of a material beforehand. And when I say beforehand, I mean without knowing what the material is even. So without knowing whether it's a metal or an insulator, without knowing, possibly without even knowing its structure, although that's a bit more challenging, to be able to model it, predict all of those behaviors. It's possible because we know that most of the properties are governed by the material's electrons. The electrons behave according to quantum mechanics, and for quantum mechanics, we can write down the Schrödinger equation and solve that. It turns out solving the Schrödinger equation directly is extraordinarily difficult. In fact, just the wave function for the electrons is huge for more than 6 or 7 electrons. Even a fairly crude model, by the time you get to modeling 7 or 8 electrons, you're talking about needing several zettabytes of data. You're talking about needing most of the data storage in the world. So it isn't possible for us to do that just solving the Schrödinger equation that you might have looked at if you did physics or chemistry as your undergraduate degree. But we'd still like to be able to do something like that, because what we really like is to be able to model the behavior of our materials directly from our simulation and just have it as an emergent property. And density functional theory comes to the rescue here. Essentially, what density functional theory proved is that there's a strong link between the problem I'm wanting to solve of all these electrons interacting with each other and moving in an electrostatic potential from the nuclei, so they're attracted to the nuclei, which has its lowest energy possible, which I've just called E here, with a particular distribution of electrons. And DFT showed that there's a absolutely equivalent system where the electrons actually don't interact with each other, not directly, and they feel the same potential from the nuclei, but there's an extra potential in there as well. And that system also has energy E and density rho. Now, the important point here is if the particles don't interact directly, then you can solve this with something that looks like a Schrödinger only for one particle, and one particle is fine. It's lots of particles that caused my problems. So if you're in DFT, you'll realize I've skated over a lot of details. If you're not in the field of DFT, probably that isn't really enough for you to understand. So the key take-home message is that we're effectively solving the Schrödinger equation, but we're doing it by solving an equivalent form that's easier. There is a catch. I said that you need to add this extra potential, this modified potential, and actually nobody knows what that should be. But there are reasonable approximations that do a pretty good job in most circumstances. And because of that, density functional theory has become probably the most common way of investigating how the electrons are distributed through a material called the electronic structure, because it's computationally very cheap compared to other methods, and yet it's actually pretty accurate. So there's a plot of the number of publications per year. This is from Bob Jones' excellent review in 2015. And you can see that we've got this sharp increase from around about 1990. Now, you might say, oh, 1990, so that's when the theory was developed. Actually, the theory was developed in the 1960s. The thing that changed towards the end of the 1980s was we actually started to get software that implemented this and put all the theory together in a usable way and that actually worked. And one of those programs that came along right at the end of the 80s was CASTEP. And CASTEP is widely used in the UK and globally. It's one of 4 of its sort of class of DFT programs in the world. And over the lifetime of ARCHER, if you looked at the monthly application statistics that used to be published from ARCHER, CASTEP went between about 5 to 15% of monthly CPU cycles. So actually it was a significant percentage of the machine. And if you add in similar codes like VASP and Abinit and Quantum Espresso, then some months we were peaking at sort of 40% of the whole of ARCHER. So this is not just interesting from a scientific perspective or a sort of idle curiosity in how does it work, but actually this is a substantial fraction of the machine. So it's worth, let's say, £6-7 million worth of ARCHER, maybe more. And similar, if we add in similar things, we're talking about £15 to £20 million worth. Right, I've attempted an animation here. We'll see if it works in a moment. Try to convince you that this isn't all sales pitch and that we can actually predict something. What I've done is I've taken a molecule here, which is an organic molecule. It's a hexagon of carbon atoms with some hydrogens coming off them, and then there's an oxygen and a sodium atom here. And the reason I've used this as my example is because the carbon atoms and actually the hydrogen, which aren't shown in this the diagram on the left, are covalently bonded, which means the electrons should go between the atoms. And oxygen and sodium are ionically bonded, so there should be very few electrons in between the oxygen and the sodium, even though they're tightly bound. And actually this hexagonal ring has a delocalized state. It looks almost metallic-like, so I would expect electrons to be sort of smeared around that ring. So I've run CASTEP on that, and I've plotted, CASTEP works iteratively, we'll talk about that in a few moments, but I've plotted the electron density in a 2D slice straight through the middle of this molecule, iteration by iteration, and I've deliberately messed with CASTEP's code to take a really stupid initial distribution of the electrons, which is what I'm plotting on the right hand side here. I'm plotting that, and I've basically given a uniform random distribution of electrons throughout a box in space, which is terrible. We don't normally say that, but just to illustrate it. Let's see if I can get this to work. So each frame of this, oh, and now it's not going to work. Can we get it to work? Okay, apparently it's not going to play ball today, even though it worked when I ran through it 20 minutes ago. Never mind. If we have time at the end, I'll come back and see if I can get it to work. But what I was hoping to show you is that within only a few iterations, in fact about 2 iterations, this random mush of electrons that you see on the right hand side rapidly takes the form of a sort of smeared out hexagon, and the blobs on the oxygen and the sodium, and the bonding emerges. That would have been more convincing if that demonstration had worked, so we might come back to that. Now, CASTEP itself, just some technical details. It's roughly speaking 500,000 lines of code in Fortran. That's non-comment code. There's probably another 250,000 lines of comments. For its performance, it relies on not just the Fortran compiler, but the BLAS, LAPACK, and FFT libraries for dense linear algebra and fast Fourier transforms. And in its parallel mode, we use the message passing interface, MPI, and OpenMP for threading. The core development of CASTEP is all in the UK. So it's at the University of York, where I am, and also Warwick, Oxford, Durham, and Cambridge. The goal of the whole project really is that you would be able to take some chemical elements and some sort of approximate configuration, and you would choose your model for the quantum physics. So this is this modified potential I alluded to. So typically one of 2 or 3 good approximations to that. You'd feed those into CASTEP, and out of that, CASTEP would tell you from your rough geometry what the optimized geometry was. It would tell you the electronic properties you want. It would tell you any dynamic properties that you'd asked for, ideally without any further user intervention. Now, this is an ambition. CASTEP has other parameters at the moment that you need to know and to tune to get the best performance, and there are other things that you might need to adjust, but our goal is that it should be just this simple. Now, when we're talking about doing these calculations on a large machine like ARCHER2, we need to run in parallel to get anything like the computing power available. And before we talk about that, we need to just have a couple of details about what CASTEP is doing. The first thing that we do is we exploit the fact materials have a periodic structure. When you look at their atomic positions, they are crystals, and so the atoms arrange themselves in regular repeating units. And for that reason, it makes sense to express the electronic states themselves, what we call the wave functions, in a periodic basis. And that means a Fourier basis, or sometimes called a plane wave basis. It's in 3 dimensions, so this is a 3D Fourier basis. But apart from that, it's just like the kind of Fourier bases, the periodic bases that you might be familiar with for music, for example, when you see graphic equalizers and you do a decomposition into the frequencies, or if you've looked into how JPEGs or MPEG compression works, it's exactly the same idea. The wave function is just a set of coefficients multiplying each of those frequencies, if you like. They're in space, not time, but it's the same idea. And it's these complex coefficients that CASTEP is trying to compute. And actually, it's the main data object as well. A little bit of terminology. You'll see that these the coefficients have 3 indices. So the one that I've called G, this is conventionally in the field known as a G vector, but it's just the index for the particular frequency that we're looking at, so the particular plane wave. In solid state physics, it's also called a reciprocal lattice vector. The second index is B, which stands for band. The band of a material is a particular electronic state. So it's a state that an electron can occupy. So you can think about that as just labeling which electron I'm talking about. So if I had 10 electrons, you can think of this as I might have something like 10 states that I'm trying to compute. And it turns out that the wave function has a kind of phase which is not strictly periodic, and I need to sample different options for that. And this last index K labels the options that I've sampled. This is related to Bloch's theorem if you've done a physics or materials background. So we've got these three indices, G, B, and K, for my main data object. What am I actually trying to do with them? Well, what I'm doing is basically an eigenvalue problem. So if you've come across eigenvalue problems in other contexts, you'll be familiar with them. Normally, they take the form of you've got a certain matrix, and you want to solve an equation where a matrix operating on a vector equals a number times the same vector. And I solve that equation to find both the vector and that number. It's called an eigenvalue problem, and that's pretty much what we have, what CASTEP is trying to solve. The only slight subtlety here is my matrix here, H, depends, it has a contribution to it which depends on all of the components of the vector, so in this case the wave function. And that means it's a little bit tricky because I don't have the matrix that I'm trying to get the eigenstates for directly. So I need to solve this equation iteratively. There's another reason why solving the equation iteratively might be useful. In a plane wave basis, it's a really big matrix. I might easily have a 1,000,000 by 1,000,000 matrix here. So if I simply gave that to LAPACK, for example, or SciPy, or your favorite matrix algebra package, it would give me 1,000,000 eigenvectors and 1,000,000 eigenvalues, these numbers. But if I look at how many electrons I might be simulating, typically I'm probably only simulating around 1,000 electrons. So I don't need 1,000,000 states. I only need 1,000 states, maybe a few extra to get what the nearest energy states are, the unoccupied states. But it's quite typical to find that I'm looking at somewhere between fractions of a percent and maybe 2 or 3% of the total states in any given simulation. So if I just give this to LAPACK, I'm wasting a huge amount of time. Whereas if I solve this iteratively, I can just target the states that I need. So if we look at the equation, I know the form of this matrix H. I'm solving to get the wave function, which I've labeled psi here, which that tells me where my electrons are in space and the properties of the electrons. And I also get this number E, and E is the energy of that state. So it tells me the state and the energy of that state. And it's that is going to tell me all the properties I need to know about my material. So solving the equation iteratively lets us focus on computing these 1% of states that we actually want. But in order to do that, the way that we do it requires applying this matrix repeatedly. And the matrix is made up of several contributions. Some of those contributions are very efficiently applied in the space of the G vectors in this reciprocal space. And some of them are very efficiently applied in direct space, real space, the space of positions. So in order to go between my plane wave space, if you like, and my real space, I need to be able to use fast Fourier transforms so that I can switch between those spaces very efficiently. And it is very efficient. It's extremely good computational algorithm. And if you're running on a laptop or a workstation, then this is excellent and you don't worry too much about it normally. So where does CASTEP actually spend its time? There are two bits actually. The first bit is what I've just said, applying the Hamiltonian. And the two bits that you might particularly notice, the kinetic energy part of this, I've written the actual mathematical part here, but it's not very important. The kinetic energy is a differential operator. It's extremely efficient in my plane wave basis in Fourier space. When I want to add in the term which is the way the electrons are attracted to the nuclei, that depends on the distance between the electrons and the nuclei, and that ends up just depending on the position of the electrons relative to the nuclei in real space. So I do this Fourier transform, and the time it takes to do the Fourier transform is n log n, where n is the number of G vectors, the number of plane waves, and I need to do that for each of my electrons, NB, with each of these assumptions about its phase variation nk. The other thing I need to do is I need to make sure that the states the electrons occupy are different. If I just try to find the lowest energy state, well, one of the states is the lowest energy one, and all the electrons would try to jump into that state, which isn't physically what happens. If you have an atom, the electrons can't all go into the lowest energy orbital. In fact, most of chemistry wouldn't happen if they did. If an electron occupies the lowest energy orbital, what we normally call the 1s orbital for an atom, the next electron has to go into the 2s. It can't go into the 1s. So to make sure that the states stay distinct, we enforce that they are orthogonal to each other. And the normal way of doing that is if you have a set of approximate states, you compute their overlap matrix and you invert it to make sure that they all have zero overlap with each other. And the time to do that scales as the number of plane waves each state has for each pair of states, which means the number of states squared. That's how it scales at each k point. So we have applying the Hamiltonian scaling like ng log ng nb nk, and this orthogonalization scaling like ng nb squared nk. So for small systems, you tend to find that the Hamiltonian time is the key one, and for large systems, the orthogonalization is the key one because it's nb squared in the way that it scales. And I've said that NB, that's dominance in large systems because of the NB scaling, because NB is the number of electrons, and that increases as I add more atoms. Actually, NG also increases as I add more atoms because I would need to add more volume to my simulation cell. And as I make my simulation cell bigger, more plane waves can fit inside it. But the number of K points, it turns out, decreases with the size. And eventually you might only have one. So for a system on ARCHER2, for example, it's quite common that the number of K points is very small, somewhere between about 1 and maybe 6. Whereas the number of bands might be thousands, and the number of plane waves will be hundreds of thousands, millions, maybe even tens of millions. So I've given you a sort of a vague ballpark figure for the kinds of systems that are routinely done on well, on Archer. We'll see what happens with ARCHER2, but I imagine it will be this and bigger on ARCHER2. Okay, how do I use lots and lots of cores then with a machine like ARCHER2 where we have 750,000 cores? Well, if I write down the equation here, and I've included the fact that H depends on the wave function here to remind us that we're going to have to solve this iteratively, you'll see that every object here is indexed with K. So actually, I have a different set of equations at each K. So one thing I could do is I could say, well, these equations really are not coupled very strongly between K. They're almost independent. So I could just give different cores different K points and let them solve it. I exploit the fact here that the orthogonalization at different K points is independent, so there's no communications there. The Fourier transforms at different K points are independent, so there's no communication there. And the only time there's communication is when I need to update my Hamiltonian matrix H, because it depends on all of the wave functions for all of the K here. But that doesn't happen very often, and it's not a huge amount of communication, so the scaling tends to be very, very good. Unfortunately, we have problems with load balance because there aren't very many K points, and the bigger the problem you try to tackle, the fewer K points you have. So although K points parallelism is really good, the bigger the simulation you're trying to do, the fewer K points you have. So if we relied on K points parallelism, we'd have a really annoying case where the more work we had to do, the fewer cores we could use. And that's not going to get us very good science on something like ARCHER2. So the other thing that we could do is we could distribute the Fourier components themselves. We could also distribute the band, by the way, but which we do in CASTEP, but I'm not going to talk about that today. I'm going to concentrate on the, if you like, the two extremes. If we distribute the G vectors, we can distribute all the data in the workload. NG is large, so load balancing is not such a problem. And as I have a bigger and bigger system and I try and simulate more volume, if you like, it increases with system size. So this is good because the bigger the system we have, the more G vectors there are, so the more scope there is to use my parallelism. It does need some extra data reorganization, but it's reasonably good scaling for small to medium numbers of cores. The reason it doesn't scale to large number of cores is because when I do my Fourier transforms, if I want to know what the wave function is doing at a particular point in space, I need to know what's going on at all of the different spatial frequencies, if you like, these G vectors. And I distributed those amongst the cores. So whenever I need to know what's happening in real space and I need to do a Fourier transform, all my cores need to talk to each other. And that's an all-to-all communication. And eventually, as you increase the number of cores, that starts to dominate, starts to hurt you. Okay, that's lots of background theory. So I apologize if that's the first time you've seen it. That's probably way too quick. Let's have a look at some sample systems. So first of all, a really small system. It's 33 atoms, 8 K points, 164 bands, and about 11,000 plane waves, G vectors. It's actually a titanium nitride surface, looking at where hydrogen likes to go onto the titanium nitride surface. It was an interesting scientific investigation about 20 years ago. It now looks extremely small. But if I plot how the time scales on a sample machine, then this isn't ARCHER2, as you'll quickly realize for the process count. The computational time goes down. I've plotted this on a log plot, so perfect scaling is a straight line here. So you can see that it's a straight line as I go from 1 to 2 to 4 to 8 cores, up to 24, it's doing pretty well up to about 96. And then slowly it flattens off. And log plots are good when you're looking for straight lines for perfect scaling. They're less good when it starts to roll off because it's hard to see just how bad that is. So I'll show you some of the later results. Show it in a. But you can see that as we go to 384 and 768 processes here, we're starting to see that first of all the calculation time stops going down, and then it actually starts to increase. And when it's increasing, what this is telling us is that the communication time is actually greater than the computational time. So as I increase the number of cores, the computational time is going down, but the communication time is going up faster. So this is a disaster. We don't want to be in that regime at all. Now, maybe that's just because this is a really small benchmark. This benchmark is taking about 40 seconds. So it's really asking a lot of a computer to parallelize over lots of cores. Maybe we should go to something a little bit bigger. This is another surface calculation from a scientific investigation onto Sapphire AL203. And it's a 3x3 surface cell here, which means we've got getting on for 300 atoms. We're down to only 2 K points. Remember, the K points go down for bigger systems. We've got quite a lot of electrons. We've got over 1,000 electrons. And actually, I slightly glossed over one subtlety, which is you can have 2 electrons in each state. So I've got nearly 1,300 electrons, and we're typically computing about 800 bands for that. And we've got around 100,000 plane waves, 100,000 G vectors. So it's a much bigger calculation. And here you'll see that we're very efficiently going well above 192. We get to 384 pretty happily, but then now at 576, we're starting to slow down. And now we're going to 1,000, over 1,000, it starts to get actually worse than it was, and 2,000 is worse again. So we're still getting this characteristic rolling over the performance. It's still going slower at large core counts. The core counts that it happens at are bigger, but it's still not ideal. In fact, I've multiplied the number of atoms by 9, going from the small case to this much bigger case, but I've only managed to multiply the number of cores I can use effectively by about 2. So this doesn't sound very encouraging for CASTEP on a large modern computer. Now, I've already mentioned why this is. It's because this scaling for large numbers of cores is dominated by all-to-all communications. The problem is every process has information for every other process. They all need to do this big swap. That means as I increase the number of cores, the number of communications scales as the number of pairs of cores, which is number of cores squared. And I've got the same total data to exchange, so that means the size of each message decreases, like 1 over the number of cores squared. And this is particularly problematic for 2 reasons. Firstly, that means that not only am I sending more and more messages, but they're getting smaller and smaller and smaller. And that means that I become much more sensitive to the network latency. For big messages, I gain if I have a high bandwidth network. I'm sending lots of data, so I care about how much you can pump through the network. But for small messages, I'm starting to care a lot more about how long it takes the system to just set up the infrastructure for a message. And because the message is really short, I'm starting to care a lot less about bandwidth. And that's a problem, because improving bandwidth is easy. Improving latency is really hard. And the final piece of the puzzle that makes this really nasty is on modern architectures, the nodes typically only have a few network interconnect chips NICs. So on ARCHER2, for example, we have 128 cores per node. We have, I think, 2 NICs, not 128. We have 2. So these n-squared communications have to be dealt with by just 2 NICs per node. So let's imagine here that I've just got 6 cores. It's not very many. I've drawn here an arrow showing the all-to-all communications for those 6 cores. I've mostly shown it so you can see that it's a mess. It's a lot of communications. But I don't have 6 cores all connected. I would probably have, let's say, 2 nodes or 2 chips of 3 cores each. So all of those communications, anything that is a communication between something on the right with something on the left or vice versa has to go onto the interconnect between the nodes, and that has to go via the NICs. So in this simple example, there are 9 messages doing that, and there are 2 NICs. So I'm sharing the NICs, and I've got to get 9 bidirectional messages through them. That causes a reasonable amount of contention. They can probably cope with that. But what happens if I go up a bit? Now, I did this a few years ago when we had 24 cores per node, and 24 by 24 is 576. I was going to redo it today for ARCHER2, but when I redid it, you basically couldn't see anything because there were just so many, because it's 128 on the left and 128 on the right for ARCHER2, and 128 squared communications across the middle. It's a lot. Okay, well, 128 squared communications in total, actually, not all of them across the interconnect here. But here we can do something using a different technology. We can split this using shared memory into 2 phases. We can gather some of the messages that are going on from processes that are in the same node, and I can pack them together into a single larger message. The total data is the same. All I'm doing is I'm taking the 3 cores worth of data and I'm packing it into one message that's 3 times as big. I then exchange those big messages, but maybe only 1 or 2 messages per node now. And then I look at what I've received from the other nodes in their big messages, and I parcel out the data that each process needs. So I've got, if you like, 3 conceptual phases. Everyone on a node gathers their data together into one message. Then one of you shares your big message with the other nodes. and then you've received some messages from those nodes, and one of you parcels that out to the other processes. So in other words, instead of having all these messages, I might have everybody passing to one sort of designated process, then those processes talking to each other. Now this is one message, but it's a big message, which means firstly, one message, so I'm not overloading the NICs with lots and lots and lots of messages. And secondly, it's a big message, so I'm really using the fact that I have a high bandwidth interconnect. And then after I've exchanged them, I farm the data back. So each of the sort of nominated communication processes distribute the data we've received back. So I've swapped one communication phase for 3, but the scaling of each of those 3 processes is better. It's the same total data. I've not changed anything about what data is exchanged or even really when it happens in the larger sort of CASTEP's flow. I can do it with explicit shared memory, either System 5 or POSIX shared memory, or I could do it by using OpenMP threads. So maybe what I labeled as master process, that's an MPI process, and the others are just OpenMP threads. There's always, whichever way you do it, there's a little bit of extra overhead in doing it, but the scaling is better. So this red line is what the performance we had before. And if I do this trick, even if I just say every pair of processes get together, or every 4 or every 6, then I get considerably better scaling. So this is what happens if every set of 6 processes group together, or in fact this was 6 threads per process here. I get very similar performance at low core counts, but it scales further, typically scales to 2 to 8 more cores effectively. That was done under an eCSE development, and we've had a large number of eCSE developments funded via ARCHER and more recently ARCHER2. So I thought it might be just as a bit of a publicity. It's well worth it if you can think of a good project. It's a lightweight way to get funding and to get some really good software development, and we've benefited enormously in CASTEP. So I have given here a sort of timeline of various things we've done under ECSEs. Actually, the first one was a DCSE back in the days of Hector. The rest are ECSEs, I think. This is the time it takes to compute a small protein, so compute where the electrons go in a small protein in water, using 500 cores of, actually this was ARCHER. I ran each of these on ARCHER. In blue, we have the time it takes to do the simulation, and the time it takes as I update CASTEP to use each of the methods introduced in these ECSEs. And you can see that overall, we've got a speed up of around about a factor of 8. In red, we have the memory as overhead, which is increasingly important and relevant to materials simulations. And you'll see that that has not improved as well by as much as the time, but it's gone down by a factor of a little bit over 2 in its RAM per node. And the biggest one is just being able to do some shared memory here. Now that's all well and good. Why would you actually want to do these simulations? What do they give you? I've said you can predict materials properties, but what good is that? Well, one problem that I'm sure you're familiar with is the world energy use and the problems it causes to climate change, for example. This is from the Statistical Review of World Energy that BP do. This was the one published in 2017. I haven't spotted one since then. This is the global energy consumption by humans over those years, and you can see a reasonably consistent trend here. Roughly speaking, we're using 4 times more power were in 2017 compared to what we were using in the mid-1960s. And all of that energy generation and transmission and usage, there are inefficiencies at every stage there, and we need to address it. So one thing that we might do, and something that I've been doing in my research group, is to use what's called the thermoelectric effect to try to recover the heat that's lost at every stage of generation, transmission, and usage, to try to recover that as some extra electricity, and that's using something called the Seebeck effect. Now, I don't have time to go into what that is. Happy to talk to you about it afterwards. The important thing to notice is that it's computable. There's a figure of merit to say how good a material is. It's called ZT. And basically, if it's under 1, it's not interesting. If it's over 1, it's useful, and the higher the better. So if we get something that starts getting into 1.4, 1.5, it's very usable, and the goal would, well, the goal is as high as possible, but a practical goal is probably to have ZT above 3 would make a substantial difference. Okay, we're a long way off getting to 3, but the higher the better. Commercially available materials that you could easily get have ZTs of somewhere between about 0.5 and 1 typically. Now recently, niobium, iron and timonide has gained a lot of interest because it can generate a lot of electrical power. So that's what we simulated using CASTEP. We simulated the electrical conductivity, that's a sigma in this equation, the thermal conductivity, that's the kappa in this equation, so the denominator, and the intrinsic conversion of the of heat to electrical power, which is the Seebeck coefficient, the S that's squared in this equation, and T is the operating temperature, the average operating temperature. So that is an input. The first thing we did is examine how the properties matched experiment. So here is the thermal conductivity contribution from the lattice. The solid lines are including different things in the CASTEP model. The red line is what we get if we include everything. And the filled circles and stars are 2 different experiments on this material. So you can see that we're really managing to model the experiment really quite well across a reasonably wide temperature range here. We can also model the ZT, and this is a color chart of the temperature, how much I dope the material, so I introduce impurities to improve the electrical properties, and then the color map is ZT. I really would like ZT of, well, the higher the better, but being realistic, somewhere around, say, 1.2, 1.3 would be lovely. And for this niobium, iron, and timonide, I'm getting a ZT of just a bit over 1. This is in keeping with early experimental findings. But because I've got a computer model, because I can predict these properties, I can start experimenting with it. And we looked at the material and thought, actually, we might be able to lower the thermal conductivity if we swapped niobium for tantalum. So we did that, and CASTEP is very easy. You delete the letters NB and you add the letters TA on your input. It's just that easy. The simulations predicted that the material was stable, so you should be able to make it. And the power factor that was very high for the first compound, which is why people were interested in it, is actually higher for tantalum. So this was immediately quite interesting, but the real thing that we're interested in is the figure of merit ZT. So we did exactly the same as we did for the niobium compound. We looked at what ZT was going to be, and we found that the ZT had gone up considerably. We get a ZT of around about 1.5. So CASTEP predicts that this material for thermoelectric applications is around 40% better than a previous material which generated a huge amount of interest because of how good that was. And as this paper was in the review process, actually someone managed to make this tantalum compound. So the results were validated as we were publishing them. So that's a sample simulation. I've gone through it very lightly, but that's the kind of thing that we can do. We can predict new materials, we can predict their properties, and they tend to match experiments extremely well. So they're reliable enough that you can design and direct experiments. But we still need to be able to use a large machine effectively. And as you've already seen, for big and complex systems, eventually CASTEP does run out of steam. So have we gone as far as we could go? Well, in the last few minutes, I'd like to say, no, we haven't gone as far as we can go. And we've got an eCSE on an ARCHER2 eCSE in process at the moment, exploring a new way to do our Fourier parallelism. The key idea is to not distribute the plane waves in the same way as before, but to distribute them being aware of where each of my MPI processes actually is in the machine, and to arrange them in a kind of logical two-dimensional grid. And the reason that we want to do that is because although I told you that every process needs to communicate with every process, and that is true, actually it can be done as a two-step process where each task only communicates with tasks in the same process row, and then you communicate with tasks in the same process column, but you never need to communicate with any of the tasks who are in a different process and column. All of their information comes to you indirectly via other communications. So your direct communications don't involve everybody. If you structure it correctly, you can get it so they only involve a subgroup of the processes. And this helps enormously in the communication cost. It doesn't help enormously in the load balancing. That is a nightmare. And for about 25 years, it was believed that you couldn't use this idea. This isn't a new idea in engineering, for example, but it was believed that you couldn't do this for calculations like VASP or CASTEP or Quantum Espresso or Abinit. But we found a way to do it. And already got some early results, which I'll show you now. So this is actual ARCHER2 data. This is for the sapphire surface that I showed you the ARCHER1 data for before. First of all, the dashed line here is not using the shared memory trick. And you can see that actually the parallel time doesn't get you very far. If you do the shared memory trick, so in this case, OpenMP threads, we've used 4 threads here, then I can effectively use 1,000 cores very well, 2,000 cores not so well, 4,000 cores, it's slower again. If we use this new idea of the process decomposition, if you like, then we get this sort of Cyan distribution. This is exactly machine identical answers to the other two. It's just faster and it scales better. So now you can see that it's doing very well performance in the small number of cores, but 1,024 it's still going faster, 2,000 cores still going faster, but even at 4,000 cores, it's still going faster. And I actually can't show you beyond 4,000 cores because beyond 4,000 cores, I have fewer than one thing to distribute. So that is as far as you can take this calculation without distributing it in an additional way, which we can do in CASTEP, but I wanted to focus on the Fourier parallelism. Now, looking at how well it scales just by looking at time is really, really hard. So I've actually done 1 over the time to say, well, how many iterations do I get per second? So this is what we get then. So if I look at that, this is basically the speed. So if it was perfectly speeding up, this would be a straight line. And this is what I get with the new distribution. So you can see that it isn't perfect still, but I'm getting very, very close to the straight line scaling that would be my ideal here. Now we're only a third of the way through the eCSE, so it's sort of relatively early days, but these results are extremely encouraging, and they suggest that the future is quite bright for plane wave DFT methods, that there are ways to really substantially improve the performance, even though they've already had about 30 years of software engineering in their performance. So to wrap up, I'd like to thank the people who've done most of the work. So Matt Smith and Ian Tamaris in Cambridge have worked on the threading and on the new parallel distribution. Ed Higgins, Matt Probert also worked on the threading, and Matt Probert and Gennady Naidenov did the thermoelectric calculations and the work there, which was published in 2019. So I've put a little reference there. And if that was too fast or you can't remember it, then my take-home message really would be you can use DFT models very efficiently on ARCHER2, on high-performance computing, to discover new materials and to predict the properties of materials new and old, really with remarkable agreement with experiment. And we can use that to tackle current issues of technological and societal importance. They're reasonably efficient and they're perfectly usable, but there's still a lot of room for improvement. And with new methods, we can get substantial performance improvements, even over the scope of something like an ECSE, which might be just, say, in our case, 12 months of somebody working full-time. With that, I'll say thank you very much for your attention. And we've got about, I guess, 10 minutes for questions and any discussion. Over to you.
Great, thank you very much. Yes, so if anyone has any questions, then you can write them in the chat box, or you can raise your hand and ask using your mic, whichever you prefer.
Oh, I can see a question from Bank. Do you want to unmute yourself?
Yes, thanks for a nice talk, Phil. Happy New Year and all that. So, in terms of the this sort of tantalum iron antimonide, was it? Do you have a structure for that?
Yep.
Just curious, what does it look like? Is it some
it's a half Heusler material. It's a bulk material. It's a half Heusler, which means it is what's the best way of thinking about it? It's just, if you imagine 4 cubes all intersecting each other. So you take a cube, you put an atom at each vertex. Okay, niobium. You take another cube, you shift it, you put it sort of so it's shifted by half vertically. You put the tantalum on there. Take another one, shift it half horizontally. That's where your antimony goes in. If it was a full Heusler, you'd do the one that's shifted in the other direction as well. But it's a half Heusler, so that's got gaps. So that's essentially the structure. So it's interlocking simple cubes.
Yeah, thanks for that. Yeah.
The Heuslers are quite interesting for a range of reasons, actually, because some of them are also half metals. So they're metals for one spin of electron and insulators for another. There's all sorts of things. And some of them are iron vanadium aluminide is also a thermoelectric half Heusler. Okay, I can see some chat questions coming in. Okay, so Bonan asks why it doesn't distribute memory well in k-point parallel. It does in a large calculation. It distributes the memory very well. The main problem is, so for smallish calculations, the problem is there are some things like the electron density which are summed over k-points. So they don't distribute by k-points at all. They don't have a k-point index. And for small calculations, that can actually be quite big. The other thing is slightly so practically you can save k-point data because they're independent. You can page those to disk, or in fact, if you're doing something like a density of states calculation, you could just work on the k-points one at a time. So if you parallelize over k-points, you've got this whole problem in memory at once. If you parallelize over the Fourier components, you can actually not bother having the other k-points in memory at once, just literally work one k-point at a time. You can't do that in the ground state calculation without storing them at disk or something, because the Hamiltonian depends on the wave functions of the other k-points. So it depends how you're running it. But the main problem people tend to have with k-points is when they're the calculation is huge, and if you try to work on all the k-points at once, it won't fit in memory. And it's actually more efficient then to work on one k-point at a time and not parallelize over them. Okay, hopefully that answers your question, Burnham, but feel free to come back. Dominic, is there a noticeable difference between System 5 and OpenMP performance? For the typical CASTEP user, would one be recommended over the other? Okay, for the communications part, the OpenMP is slightly quicker, usually. That's because in the OpenMP, the other threads are sort of sneakily reading the master thread's memory. So although I broke it down conceptually into 3 communication phases, actually they're sort of hidden because the data mostly stays with that master process. With System 5, they do genuinely all have their own memory and they are copying it around. So in the communication, the OpenMP is faster. However, in the rest of CASTEP, the MPI is leaner and more efficient than the OpenMP. So actually, it's not a straightforward comparison. I could have shown you I have data for the difference for the AL3x3, for example, in ARCHER2 that I can share with you later if you like. And that is, it's a little bit more subtle how you do that. So OpenMP, the take home is probably for moderate process counts, the System 5 shared memory is better. For large process counts, the OpenMP is better. For 2 reasons. One, the communications are slightly faster, as I said, and the other is OpenMP offers some extra parallelization possibilities in operations. So for those of you who know CASTEP, you can thread over the non-local pseudopotential projectors when you're doing things involving those, for example, which is an additional parallelism that you don't have available in MPI. So the recommendation is a little bit awkward. I have a different project at the moment to automate this by, we have a little mini benchmark that benchmarks the 2 different methods and tries to choose it, but it's not quite reliable enough. But we are looking at that. Okay, Alberto says, how difficult is it to enable shared memory parallelism? Yeah, so if you set OMP num threads, that works. The only catch is that enables threading in anything looking at that environment variable. So we've also enabled CASTEP num threads, which will basically thread everything in CASTEP, but not anything else. So you might turn threading on somewhere else, maybe MKL num threads or OpenBLAS num threads, or whatever it is you wanted to thread, but it lets you do them independently. That's how you turn it on. To get the best performance on ARCHER2, you need to look at where those threads will be distributed, and I find that the block distribution is the best. That is on the wiki, I think, for you when you do hybrid OpenMP MPI. That's in the ARCHER2 documentation. But do look at that because it's not straightforward. I also recommend you make sure the OpenMP threads aren't put to sleep by the operating system when they're not being used and they stay active. And that's controlled by an environment variable called OMP wait policy. So I would say look at, for performance, look at actually 2. Let me just put this in the chat. So look at these 2 as well. They're 2 environment variables, so probably something like OMP wait policy active, OMP proc bind cause was probably what you want. That's nothing to do with CASTEP. This is OpenMP and how to get performance. Okay, any more questions? I'm aware we're at 4 o'clock. I mean, I can hang around for 5 minutes or so if people do want to ask anything else. But obviously, if you want to head off, that's absolutely fine.
Thanks for the talk, Phil. Can I just ask about how much of what you've said carries over to hybrid calculations as opposed to local ones? But,
when you say hybrid, do you mean non-local exchange correlation?
Yeah, exactly.
Kind of hybrid, right? Okay, because we also use hybrid for OpenMP MPI as well.
Yeah,
I think. Yeah, so it makes a much bigger difference to that, a huge improvement, because when you do when you do a non-local exchange correlation calculation, so something like screened Hartree-Fock or PB0 or something, then you are doing a lot of fast Fourier transforms. So the fast Fourier transform goes from being a little bit of the work that is annoying because the communication cost gets big, to a huge amount of the work that's absolutely disastrous because the communication gets so big. So my scaling, the transformation in scaling is absolutely revolutionized by the new work. That it's so much so that I'm embarrassed presenting that, which is why I stuck to semi-local DFT today, because it just looks almost unbelievably good. It's actually a similar story with other things to accelerate, like GPU work. The non-local exchange correlation is very sensitive to your FFT. If you can speed your FFT up, then you just win by an enormous amount.
Oh, that's good to hear. So you say maybe in about a year there's a potential that the hybrid calculations could get a lot better.
We're hoping to so actually, although I said it was a prototype, we prototyped it to show that it worked for the eCSE application. We've developed the prototype as part of the eCSE into something that now we're very happy with, but isn't as flexible in terms of core count as we'd like. But if you're willing to sort of choose your core count with slightly more care than normal, it's already perfectly usable. If anybody wants to play with it, we could make a beta version available.
Oh, well, that's good news. Yeah. Thanks.
You're welcome.
Okay, great. Thank you everyone for coming for this webinar, and thank you very much, Phil, for giving it. It seems like there was a good number of questions there as well, which obviously is always a good sign.
Yeah, it's nice to hear people. Thank you